My name is Dexter, and I'm the solution engineer in Keysight Technologies, covering for most of the Keysight Pathwave design software. So thank you for attending today's session. And today I'll be introducing to you um, the RF circuit design and simulation software that we have in Keysight Technologies, mainly the software called ADS and RF Pro. ADS and EM Pro. Okay, so we'll go through some examples and application and see and really understand how ADS as a circuit design simulation tool, how these two can help you to be, other than doing circuit design, the main goal of this kind of ADS circuit design tool is to really help you to be successful, help you to first to market either your products or your research topic. Our tools here really helps our users to be more efficient and getting the results that they want. All right. So before I go into the details on what are the topics that we're covering on today, I just wanted to highlight that in Keysight, we offer a end-to-end solutions across the workflow and market. So for Keysight, we do cover a wide range of industries like the commercial communications, semiconductors, automotive, aerospace and defense, and so on. And for Keysight, we actually provide an entire workflow all the way from the design to prototype, test, and then eventually optimize. All right. So to cover this kind of workflow, we have solutions for both software, hardware, as well as services. So today, the team here, for myself, I'm coming from the design software part, which is really at the beginning stage of your workflow. And design software is really important because through the use of design software, you are able to determine whether your design has any potential issues or even, really understanding some design insights before you really produce your product or your research topic on that. All right. So this is, the solutions that Keysight really can offer, really the end-to-end solutions across the different markets here. And diving into just on the design software solutions that we provide, we do cover a few, I would say, segments as well, such as RF microwave, which is the main topic for today. We do have solutions for high-speed digital as well. In case you're designing high-speed digital boards, looking into DDR5 or PCIe applications, we have that as well. System level design, if you're looking into RF link budget, we have solutions for that. Power electronics, if you are designing DC-DC buck converters or phase shift inverters, we have solutions for power electronics. Likewise, for device modeling as well, if you're looking at model extractions, we have solutions on that. So for today's webinar, we'll primarily focus on just on the RF microwave topics. But if you're interested in the other solutions that we have, feel free to reach out to the Halia Tech team or even Keysight. We are able to share with you more on the other solutions that we have. But for today's webinar, we'll focus on RF microwave. We will look at ADS, mainly on MMIC application, but do take note that some of the features are also applicable if you are looking at RF PCB board, for example. It's also applicable. We'll look at RF Pro, which is part of the ADS software. We'll look into that as well. And then we'll also look at some examples on EM Pro, which is on our 3D EM software simulation. All right, so these are the main, I would say, 3 features that we'll look at to see how these two can really help you to be more efficient and more successful when it comes to circuit design, EM, and EM simulation. Okay, so for today's agenda, we'll look at 3 examples, in fact. So today's webinar will be a little bit long. We'll look at IC design workflow with Pathwave ADS. For this, we'll also look at RF Pro as well. So for the example we'll be looking at is an MMIC PA design. Next, we'll look at a rectangular design. Rectangular means that we'll be looking at a antenna design. In this case, it will be a patch antenna design using EM Pro. After which, we will then look at how we can actually do a rectifier circuit design using ADS. Basically, we can pump in an input power and kind of see, what is the DC voltage that is at the output or at the load after going through some of the diodes here. And then we can look at how we can actually integrate both the antenna design in EM Pro and the rectifier circuit in ADS, how we can actually integrate together and do a full EM simulation on that. So we'll be discussing on that. And the last example will be a quick introduction on some of the EMI and EMC use case using EM Pro. This part will be a little bit short. I would say this two part will be more intense, all right? And after which we'll then sum off with a conclusion. Okay. So yeah, let's come to the first topic about looking into IC design workflow using PathWave ADS. So before we dive into that, what is ADS? ADS is one of our RF and microwave design software that really covers a wide range of application. So you can do MMIC, you can do RFIC, you can do module design, you can do package design, you can do RF PCB board design. Likewise, you can do high-speed digital design using ADS. There's one more which is on power electronics device that is also part of ADS. Okay. So we're seeing on the right side that is a quick look at the user interface of how ADS would look like. You can see that you can actually do like this kind of schematic design, layout design, EM simulation, looking at current density flow, and really looking at results using our data display. Okay. So when it comes to MMIC solutions, we really provide an integrated workflow for our IC designers here. So definitely we have some of the best-in-class RF circuit simulators, especially for power amplifier design. If you are looking into non-linear simulation, we have the harmonic balance simulator for you to look at some of the non-linear performance of your power amplifier design. Okay. We also have some of the wireless verification test bench. We call it the virtual test bench, whereby you can simulate some of the modulated signals such as Wi-Fi, 5G signals, and you can simulate across your power amplifier design to look at some of the EVM performance. So that is one feature that we'll look at later on. Foundry design kits and models. So we do partner with some of our foundries like Global Foundries, TSMC, WinPDK. We do work with them to actually provide some of the design kits that you can use for your circuit design. Some other vendor component models like Murata as well, we do work with them, and you can actually use those Murata components as part of your circuit design as well. Okay. And then we have the backend design flow. Basically, whatever you have designed on your schematic level, you can actually do design synchronization into the layout, which I'll cover more on that as well. So you can do layout drawing in ADS, you can then do EM simulation, smart mount. This is on multi-technology. So for example, if you have designed an IC chip, you want to mount it on the packages, connected with some bond wires, we do have solutions for that as well. Okay. So that is on the back-end design flow. And then for IC design, electrothermal or thermal simulation can be quite critical. Thermal effects can affect the performance. So we do have solutions for electrothermal simulation, but we don't have time to cover on that. So yeah, if you're interested to let us know, we can do a separate demo for you. And then the last part is integrated planar and 3D EM circuit co-simulation with RF Pro. I would say RF Pro is the main highlight for today's webinar. With RF Pro, you can see and really understand how EM simulation can be easily set up very quickly. You don't have to take much time to set up EM simulation, and how you can really do EM circuit co-simulation very seamlessly and easily. All right. So this slide really summarizes the full workflow from schematic all the way to layout. and then do a full EM simulation on that. Okay. So this is just a pictorial image, some virtual image to sort of let you understand what we have discussed early on. Basically, to sum it up, ADS support the technology assembly, so you can really integrate different designs, different IC chips onto the packages and integrate with bond wires and so on. Once you have this kind of full design, you can do harmonic balance simulation, you can do EM simulation, do layout verification, and really look at this kind of performance, like looking at the spectrum of a modulated signal, for example. Okay, so this slide here gives you a more pictorial image of some of the capabilities that ADS can do. Okay. Um, so I think there's a question on sharing this slide. Definitely, towards the end of this webinar, we can share this slide to the attendees here. Okay. So yeah, this is also another key point that I wanted to highlight. The key value that ADS is really able to provide you as a circuit designer. We do provide integrated solution from the pre and the post layout analysis. So as a starting point, right, as a circuit designer, you might want to start creating circuit at the schematic level. Okay. So we have tools for you to actually create your schematic design. And once you know you have finished your circuit design setup, you run the simulation and verify that, all right, at the circuit level, the design performance looks good. The next step is to start moving into layout. So we have the feature called the design synchronization, which can help you to, move everything that you have designed in schematic, able to move it to the layout portion and do your layout design. Okay, so this is the layout design. And once you have finished your layout design, you can start to do the EM simulation. So today's main highlight again is on RF Pro. You're able to give you a 3D view and start to quickly do your EM simulation setup here. So once you finish the EM simulation setup, that's where you run or export the EM simulation results back to the schematic test bench. Either do a S parameter simulation results again with your EM simulation or harmonic balance, or simulate it with a 5G signal. You are then able to look at the results through our data display. One good thing that we often hear from our users about our data display, which you are seeing right here, is that you are able to do post-processing. So whatever data you have from the S parameter simulation results or the harmonic balance simulation results, you are able to do post-processing through some of our equation-based sort of features that we have in data display for you to manipulate and do post-processing. Okay. So for the results, anything that you see is causing issues, you can always go back to the schematic or the layout to actually modify your design and rerun EM simulation again. So everything is very integrated. Everything can be done very smoothly. Later in the demo, you'll see how it can be done. And this is really one important slide that I hope we can bring back with you today. Okay. Right. So this is on the integrated solution workflow. And then, yeah, we're going to start looking at the demonstration for the IC design here. So I would say this is typically one example of the IC design workflow that we see commonly within our users, which I'll go through in details through the next few slides here. But we'll first start off with a DC analysis, kind of understand the IV curve of the transistors that we want to use for our design here. The next part is we can start to look at, how we can optimize some of the stability and impedance matching network to get our desired results. For example, low noise amplifier, we want to do impedance matching at both the input and the output load, right? So we're going to look at optimization. So the first two steps are really could be looking at using ideal lump components. But the actual case, we're going to use the Foundry's PDK models here, the actual Foundry's component here. So we can translate into that. And that's where, once we have set up the PD components, we do a design synchronization to shift from whatever we have designed from the circuit level to the layout. Okay. And then we start to define the substrate, and then we can start to do the EM simulation using RF Pro. We can do a little bit more advanced, right? If you're going to, the end goal is to simulate this kind of PA switch module on the laminate board. We can actually do smart mount, whereby we can integrate, the different IC chips onto our package here or our laminate board. That is something a little bit more advanced as well. And then, once you have do an EM simulation, everything is done, we can really do a validation, whereby we can simulate harmonic balance to look at the non-linear performance of our PA, for example, or even simulate with a 5G signal. Okay, so this is I would say, a typical workflow when it comes to IC design. And this workflow here, definitely, this is something that ADS is able to do. Okay. So as mentioned, the first step is to look at DC analysis here. So what you're seeing here is basically this is a sort of like a template setup that ADS has for you to quickly set up your DC analysis here. And right here is an example of a transistor that I'm taking from a foundry PDK or from a demo PDK that we have here. And what we are doing here is in this setup here, this is a sub-circuit component. If we dive into what this curve tracer really consists of, you can see that it consists of the biasing circuit of VDS and VGS. So what we are doing here is a voltage sweep. Okay, so we sweep from these parameters here. And once we run the simulation, we can really, look at the IV curve of our transistor, kind of understand what is the drain current versus bias current performance, the power consumption, and sort of determine what would be the VDS and VGS that will be good for us to operate for our design here. Okay, so we have quick templates here. All right, so this fat curve tracer was coming from a template here. You just have to, select the template that you want and just place it on schematic, and then you can quickly run the DC analysis. So this setup here, I think it took me about probably just 1 or 2 minutes to quickly just place the template, insert the transistor, and just quickly run the simulation. Okay, so you can create this kind of results very quickly with the DC analysis. Okay, so we have sort of understand what kind of VGS and VDS value that we need to bias our transistor. The next step is to sort of start to create the biasing circuit or the stability circuit or impedance matching circuit here. So I classify them as sort of like optimization of circuit. So some of the tools that that ADS have to achieve, creating this kind of various circuit here. So for impedance matching, we have the Smith chart utility tool right here, whereby you can just define the input load impedance and the source impedance and define the frequencies that you want for impedance matching. And yeah, later I'll dive into details, but with the Smith chart utility tool, you can see that how impedance matching circuit can be created quite automatically for you, and you can directly use it in your simulation. Okay. For stability, I would say optimization would be the main tool to use that. So ADS have the optimization capability for you to optimize different circuits and eventually, look at, eventually the optimizers will determine the desired lump components or the desired component values that you need in order to achieve your goal here. So on the right side, you can see that we are optimizing the noise figure of the power amplifier. We are also optimizing the S21 of the amplifier design as well. Okay. One thing to note is that ADS also have this kind of quick components for you to quickly measure parameters such as your stability of your power amplifier, knowing the K factor of your power amplifier, or knowing the maximum gain of your amplifier as well. So we have this kind of quick component tools that help you to do your measurements for your simulation design very quickly. Okay. So yeah, with that, we're going to look at stability optimization. So this is some network that I sort of created, have a rough idea that, okay, probably my stability network will consist of resistors and a few inductors here. And towards the load, is connected with a resistor and capacitors. So this is just really an initial stage, kind of sort of really creating a stability circuit here. So once I've, indicated my, placed my lump components here and connected with my transistors, yeah, this is also the VDS and VGS, VGS and VDS biasing values that I've determined earlier on for my DC FET. So yeah, once I place the stability network, that's where I want to do optimization here. So this block here are some of the components that I've created for optimization. I define the goals that I need. In this case, my goal was K factor to be more than 1. All right. And then I run the optimization. And then you can see that eventually the goals are being satisfied during my optimization process here. So this is the optimization for the K factor of stability. You can see that the red portion is the limit line that you have set. In this case, I set it to be more than 1.05. And you can see that the dotted line was the initial stability of this design here. After optimization, you can see that it's automatically tuning the parameters of my circuits. You can see that eventually the solid line here, this is the final results, which is above my limit line. Okay. So you can see that ADS is able to do optimization for you as well. Okay, so now I'm done with creating the stability network. The next thing is I want to start doing impedance matching for both my input and also my output. So what I've done here is I've used these two components, which helps me to measure my simultaneous input reflection and also my output reflection coefficient. Why do I do that? Because I need to use these values to actually do impedance matching. Okay. So this slide here shows the results after my optimization for stability. I think you can see from this plot here, this is the K factor stability plot. Okay, so we make sure there's more than 1. And then the next step is impedance matching, right? So you can see this is the results of my input reflection coefficient and output reflection coefficient that I need to do impedance matching. So I capture this value at 2 gigahertz and I'm going to do impedance matching at 2 gigahertz, which is the next step. Okay. Okay, so how do I do impedance matching? Well, for ADS, we actually have the tool called the Smith chart utility. And the Smith chart utility tool actually work with this smart component here. So basically, this smart component will basically contain the impedance matching circuit that you have designed using our Smith chart utility tool. Okay, so just a quick illustration. Basically, what I did is I defined the gamma values that I've measured earlier on. If you remember my previous slide, I've measured the required gamma values that I need for impedance matching. I then use it for my Smith chart utility tool, define the impedance, and then what I can do is I can create a auto 2 element match and create that matching network for me very quickly. Okay, and then select the topology that I want for my impedance matching, and then this matching network will get updated into my schematic here. Okay, so I won't go into details, how to set up and everything, but basically I've done it for both the input match and also the output match. And after I've done the impedance matching, I rerun the S parameter simulation and kind of see, whether am I successful with my impedance matching at 2 gigahertz. And this is the results. You can see that, my stability of my amplifier is still above 1. That is what I need. And you can see that looking at S21 now, I have quite a peak of my gain at 2 gigahertz, which means that I successfully sort of do impedance matching quite close to 2 gigahertz. Likewise, you can look at the S11 and S22 of my Smith chart here. Okay. So yeah, we have tools for you to quickly create your impedance matching network. This is just on narrow band. We also have other tools for broadband as well, which I don't think I will have time to cover today. So yeah, do let us know if you're interested in broadband matching network simulation. We can share more with you on that. Okay. So yeah, we have completed doing impedance matching. And the next step is to really use the design kits from the foundries on vendors. That is the end goal. So for the stability and impedance matching, we are initially using lump components, ideal lump components, but in actual case, we need to use the foundry's PDK. All right. So unfortunately, I don't think there's a quick way. So what I did was, just replacing those components manually and create this design here and do a S parameter simulation. Okay. One thing you might have noticed is that if I compare it with the ideal components and the PDK components, you can see that the peak is not really centered at 2 gigahertz because of how ideal components can be sometimes different from the actual foundry's process design kit component here. So what we're going to do is we're going to do some tuning to actually fine tune our process design kit circuit components to make sure that we get a better S21 performance results, for example. Okay, so for ADS, we do have the tuning capability for you to actually tune your results here. Okay, so if you take note on that, initially with the foundry's process design kit component, I'm getting S21 about 13.2, right? So with the tuning feature, I can tune my results. Basically, I'm tuning the resistors and my inductors number of turns here, for example. You can see that basically I fine-tune the results to get a higher S21 performance of about 14.6 dB. Okay. One thing I wanted to highlight about ADS tuning capability is that when you do tuning, the results get updated very instantly. Okay, meaning that you don't have to rerun the simulation. As you tune the different circuit components, ADS will update the results for you and for you to do comparison. Okay, so this tuning is quite a popular tool within our users as well to fine tune the design. Okay, so after tuning, this is the updated results, and then we can use it for our final design here. Okay, so definitely tuning can help to improve results. I think initially it was 14 or 13, but after tuning, we are able to get a better S21 results. Just, slight fine tuning here. Okay, so yeah, I think we are pretty much done with, fine tuning everything. The next step is, we also need to include some of the microstrip line component to complete the design. So this microstrip line here that you see, right, it's a little bit small, but you can see there's some transmission line that's added in between some of the circuit components like your transistors and your inductors. Okay, so we are using the foundry's microstrip lines as well for our design. So this is the complete design that we have for the first stage, all right, together with the PDK transistors, circuit components, and the microstrip line. And when we do a S parameter at this level here, sometimes the results might shift a little bit because now with microstrip lines, things will gonna shift. Again, make use of tuning and optimization to actually fine tune your results. And so this is the finalized results that we get for our design here. Okay, so now we have created everything, right? We have included the microstrip, the DC bias, the circuit components. I think there are some VRs that we even included, to connect to the ground. The next step is to really combine it, to move to the layout here. But before that, I just wanted to highlight that the next part of the demo, the actual complete design is actually a two-stage amplifier design. Okay, so previously the previous features that I've highlighted is just on single stage to just show you some of the capabilities that ADS is able to do. But the actual demo design that we'll be working on, looking at EM simulation, is actually a two-stage amplifier design, whereby you can see that there is two FET networks, and we can actually do impedance matching using the Smith chart utility tool for the input, the intermediate, and also the output match as well. Okay, so this is the final design. And and then we can do a schematic simulation to sort of understand what would be the performance for this two-stage amplifier. So for this two-stage amplifier, you can see that the gain is definitely doubled, and now we have looking at 27.8 dB for S21. The stability factor is still above 1 at 2 gigahertz. We can look at the maximum gain. We can also look at noise figure as well. I think for some of the PA designers, noise figure is a critical parameters. So for S parameter simulation, we are also able to look at the noise figure of your design here. Okay. So this is the two-stage amplifier for the schematic. The next part is we're going to move to layout. Okay. So as mentioned earlier, ADS have the design synchronization capability, whereby whatever you have designed in schematic level, you can quickly shift it to the layout portion. Okay. So this is the design synchronization option. You can directly, just update the layout, just import everything into the layout, and ADS will create for you. Alternatively, you can actually place components individually into the layout. This will be a more organized approach. I won't go into details, but basically, yeah, this is the design synchronization for you to make sure that whatever you have designed on schematic level, it get retained in the layout portion so that nothing goes wrong. Okay. So this is on the design synchronization, and once you have done, performing design synchronization, this is the final layout that we design for our PA. All right, you can see the transistors, the inductors, the capacitors, they are all based on the PDK models. Likewise, we also can create the substrate. So in ADS, we have the substrate editor that you can also edit some of the materials, for example, or the thickness of your substrate. All these are editable. And we're going to use this two information for our EM simulation next. Okay. So yeah, let me just pause a while to see if there's any question. So I think one of the question raised was the Keysight produce experimental modules for research in universities. I would say at least for ADS, we have some examples that you can look at. Alternatively, definitely on IEEE website, for example. Definitely there are a lot of research papers that leverage on ADS to do your to publish those papers, using ADS to publish those papers. So definitely we have some examples that is available in ADS for you to look into it. Yeah, so definitely we have some examples for you. Okay. So I hope that addressed your question. Okay, so a lot of technical content. Now that I've answered the Q&A, let's go back to our slide here. We're going to look at how we can do EM circuit co-simulation for our PA design here. So what we heard over the years when we talked to some of our circuit designers is that EM simulation can be challenging. Why? You can look at this diagram here, right? After we have created the layout, the next thing we need to do for EM simulation can be quite tedious, stripping off the circuit components, placing the necessary ports so that you can characterize the transmission line, and then reassigning of material information. And then once the EM simulation is done, you might need to import and reconnect the circuit and EM as parameters in ADS. So very tedious step, very time consuming. Likewise, connection, manual connection for your EM and circuit co-simulation result can be very tedious, very error prone. So many wires, it gets very confusing, right? So this is something that we heard from our users, and we came up with a solution, which is the key feature that I really want you to bring home today. And the tool that I would like to introduce to you is RF Pro in ADS. Okay, so the key benefit of RF Pro is that basically we don't have to do all this step. Okay, later in the demo, you'll see that RF Pro really helps you to be more efficient when it comes to EM circuit co-simulation. You'll realize that the EM simulation setup is very easy. You can quickly set up your ports and you can quickly run your EM simulation on that. Okay, so RF Pro is really the main tool that helps you to be efficient when it comes to EM circuit co-simulation. Okay, so some of the benefits that I would really want to highlight to you, rather, some of the benefits that I really like about RF Pro personally is that you don't have to do cookie cut. For PCB designers out there, sometimes you might be working on large PCB boards. And sometimes you just want to simulate just one portion, maybe a filter design portion on the PCB board that you have created, after your layout, right? You just want to simulate a portion of a board here. So with RF Pro, you don't need to do cookie cutting because RF Pro have the specific nets analysis that you just have to specify what you want to simulate on your board. And at the background, RF Pro will do that automation cookie cutting for you. Okay, so you don't have to do cookie cutting. You don't have to manually remove or place your transistor device, or if you have S parameters that you need to bring in for your simulation, uh, we have a quick way for you to do it. Just import and the connection will be done automatically for you. Okay. This is one point that I really like, which is no expert setup and be confident in the setup of your simulation and accuracy of the results. These two are some of the common key benefits that I also hear from my users as well who are using RF Pro. It's really very easy and you are more confident when it comes to EM setup. And then for RF Pro, it's a solution for PCB, RFIC, MMIC, RF modules. This is also one thing I wanted to highlight. RF Pro is available not only just in ADS. If you are already using Cadence Virtuoso for RFIC design, for example, RF Pro is also available in Cadence Virtuoso. We recently also collaborated with Synopsys, their custom compiler. So you can also use RF Pro in the custom compiler environment, okay, for your EM simulation. All right, so do take note on that. Not just on ADS, RF Pro is also available in Virtuoso and also custom compiler. Okay. So with that, for RF Pro, I think I want to show you the magic for a live demo. So let me just get out from the slides and we're going to look at ADS for demonstration here. Okay. So what I'm seeing here is the layout that we have discussed earlier on, which is the two-stage amplifier. And I also have the substrate already done. Usually the PDK will have the substrate information for you. So this is a substrate that I'll be using for my EM simulation. Okay. So once these two are done, likewise the ports, I think some of the pins here, I've already placed them on my layout. So this is where I will connect some of my RF input signal and also my DC bias. Okay. So once I have the layout done, that's where I would launch RF Pro. Okay, for my EM simulation, which I've already done it. So what you're seeing here now is the RF Pro GUI. This is the same GUI, be it you're using in ADS, Virtuoso, or custom compiler. Okay, so you can see RF Pro gives you a 3D view. Okay, and you can see that on the left it has the nets for your layout. Okay, so depending on your nets, you can actually define the nets, whether is it a power net, is it a ground, is it a signal. The reason why we are doing this, we define the signal nets, is that so that when we do port creation, it helps us to do some automation, so that you don't have to worry about making mistakes when it comes to port setup here. Okay, so in this case, if I look at P2349, basically they are my input ports here. Okay, so I define it as signal. So this is on the net, and then the components, all the components that has been defined on the layout, all this has been brought into RF Pro. And in this case, for my FET here, I want to define it as a circuit component, right? We don't, the FET usually is removed from the EM simulation portion, and then we connected it after the EM simulation is done. So basically what I did here is I defined it as a circuit component, okay? For the rest, like for example, inductors, which is have the number of turns here, I definitely need to simulate as a layout here. So definitely I can set it as the layout so that you simulate this coil here. Okay. Yeah, so this is on the components, and then for the substrate that you've seen earlier on, all the metals, the dielectric properties has been brought into the RF Pro environment for your EM simulation. Okay. And then the pins here, the pins which we have defined in layout, all these are created as well. We do support virtual pins such that, if let's say you want to create an additional pin on the layout, you are able to do that as well. Okay. Reference pin or cover, because I think due to the substrate, there's some, we are able to take the ground cover as the reference. Okay. So yeah, this is the project window or the properties window. The next thing is we're going to set up the EM simulation. So this is where you really see the key value or the magic of RF Pro, whereby EM simulation can be set up very quickly. Okay, so I'm going to create a full EM extraction. Okay, and then I'm going to first set up the ports. Okay, so the ports are usually coming from the pins. Very easily, you just have to do a drag and drop, and the ports are automatically set up for you. And if you take a look, the positive pin and negative pin has all been set up for you. Okay, and then we can actually highlight all to sort of understand, the positive and negative has been set up for you. Okay, so that's it. We are done finishing setting up the ports. Very quick, right? The next step is that we're going to set up the component models. Okay, so we can take a look at the component models. We need to tell RF Pro that, during the EM simulation results, can RF Pro help us to automatically remove this fat component, automatically place the necessary pins for the EM simulation, and after the EM simulation, RF Pro can help us to reconnect back. Okay, so what we'll do here is, again, I'm just going to do a drag and drop, only define circuit component rows. Okay, and then we are done with setting up the component models for the transistor. One thing I wanted to highlight is that you can double click on this and you can see that basically this transistor model here is based on the library cell. This is from the PDK models that we typically get from foundries. Okay, so this is the library cell. But if you have your own S parameters or SPICE model file, or you just want to use a simple lump component, we are able to add those models in as well. Okay, when you do that, meaning that you don't have to, reconnect those components automatically. RF Pro will do it everything for you. Okay, so just define what model you want to use, and RF Pro will do everything nicely for you. Okay. Okay, so now we are done finishing setting up the component models. The next thing is to define the frequency components. The frequency suite. So in this case, I'm doing a frequency suite of 3 gigahertz, 0 to 3 gigahertz. And if let's say you're interested to look at some of the current density flow of your design, you can, activate and select looking at near field plots. If you are doing antenna design, okay, know that ADS you can do antenna design as well, which I'll show you later on. If you are interested to look at far field for your antenna design, that is also supported as well. Okay. And then some advanced settings, which I will not go through in details. For the EM engine that we do support, for Keysight, we do support the Momentum and FEM engine. Okay. You might be wondering why you are saying HFSS. For those of you who are familiar with HFSS engine, Keysight, we recently also partnered with ANSYS to have the HFSS engine to be available in our RF Pro simulators as well. So we call it the RF Pro HFSS link. Okay, so if you want to use HFSS engine as part of your EM simulation, we do have that as well. Okay, so for this demo, I'm running on Momentum, and then we can then start to run the simulation, which I've already done. So you can look at results like, for example, the mesh of your design here. I think it might take a while. Yeah, so you can see how the mesh are being generated for your simulation. The S parameters as well. I won't go into details. This S parameter is just the EM. Is without the transistor yet. So there won't be any gain if you look at the S parameter results. We can look at the TDR, DDT, near field as mentioned earlier, and far field. Okay. So yeah, I think this is the setup for RF Pro. Hopefully you really understand how RF Pro can really help you to be efficient and confident when it comes to EM setup here. Okay, so before I end off RF Pro, there's one more important thing. that RF Pro can help you to be very confident and very efficient when it comes to EM circuit co-simulation simulation, which is this portion, generating sub-circuit. So this function here basically export whatever you have done your EM simulation results back to your schematic level and connect it with your test bench here. Okay, so when we generate a sub-circuit, there are two things that are created, right? Let me show you. So when you generate a sub-circuit, basically we have this schematic here being set up for you here. So in this schematic, you can see that it contains the ports that I created with RF Pro. If you remember that, very fast, easy port creation. Remember the transistor model that we defined as circuit is, and we also have the EM simulation results of our tracers, our microstrip line, our inductors, our number of inductors coils here. So this is the S parameter results of the EM simulation. And you can see that RF Pro already do that connection automatically for you. Okay, so these are some of the signal nets which connect your transistors with your EM simulation results and together with your ports. So all this is done automatically. You don't have to do anything. Okay, very efficient. So this is one thing that RF Pro create. The next thing that RF Pro create is a symbol. Okay, so the symbol is for you to actually connect it with a test bench for you to do your S parameter simulation or your harmonic balance simulation. So how this symbol is being used, let's take a look at an example. So what I've done here is I already have a test bench. Okay, so this is another symbol representation. Okay, you can see that I already have this test bench ready, whereby I have my S parameters and my other components to do my measurement. So if I take a look at this symbol right here, okay, if I do a push into hierarchy to kind of see what is inside this symbol here. Okay, if I do a push into, you can see that it contains my RF Pro EM simulation results. Okay, so if I pop out, means I go back to my test bench and I do a S parameter simulation. Basically, I can start to, sort of compare the results between RF Pro and my schematic simulation. Okay, so definitely if you take a look at, let me just zoom in a little bit. Initially, the schematic simulation, is about 27.8, but with the EM simulation, it starts to drop a little bit. This is kind of expected, right? Because EM simulation gives you a more accurate and realistic results of the design here as compared to the schematic results. So definitely EM simulation, I think when it comes to high frequency, skin effect starts to come in, coupling starts to come in. So definitely you'll see some losses in the S21 results. Okay. So yeah, you can see with RF Pro how easy it is, for you to do your EM circuit co-simulation. Set up your ports within a few seconds, set up your components within a few seconds, export your EM simulation results within a few seconds and connect it with your test bench to look at this kind of results here. Okay. So yeah, some other things that we can work around with this kind of generated sub-circuit is to perform a non-linear harmonic balance simulation here. So we can take a look at another test bench. This is another test bench whereby we're going to do a non-linear simulation here. Again, I have the biasing circuit, and now I'm going to actually have an input power that is connected to my RF Pro EM simulation results. Okay, so if you're not sure if this is really the RF Pro EM simulation results, again, we can do a push into hierarchy to take a look. Again, this is our RF Pro generated sub-circuit. Okay, so we are using the RF Pro simulation results. And then we can set up this harmonic balance. And you can see this sweep plan here. Basically, I'm doing an input power sweep to kind of do a 1 dB gain compression analysis. Okay. So again, this setup is from ADS template. If you are curious, you can see that we actually have templates that you can quickly set up your harmonic balance simulation. So basically, this is the template that I'm using from the ADS template here. And then I can just set up the simulation within a few seconds, and then I can start to run the harmonic balance simulation. So if I take a look at the harmonic balance simulation, this is the results that I get. Again, the template plots the results, everything for you. You don't have to do any manual work. And all these templates here are based on equations. So this is where the post-processing comes in. If you remember at the beginning of my presentation here, the data display are function based on equations. So you can always use equations to manipulate the data and get the results that you want, or even do post-processing. Okay, so this is on the equation base. So coming back to results, you can look at different results like, what is the transducer power gain, where does the 1 dB compression point, how are the harmonics of your how are your harmonics being generated from the power amplifier design. Okay, so we're looking at 2 gigahertz. There is another results that you can look at is the 1 dB gain compression data. Okay, so this is the 1 dB gain compression data. It defines for you at 1 dB, you know what is the gain and what is the output power that you get. Okay, so this is one test bench that you can work with RF Pro, which is on harmonic balance. Another test bench that we can look at is simulating with modulated signal here. So I have this test bench here. I call it the VTB. Okay, so what you are seeing here is basically I'm simulating a 3GPP LTE base station transmitter signal. Okay, and it's based on a ETM11 test model from the G3PP standard. And this modulated signal is based on FDD having a bandwidth of 10 megahertz. Yeah, so these are some configuration for the LTE signal. We do support for, if you are looking into Bluetooth signal, Wi-Fi signal, we have different signal standards that you can do this kind of virtual test bench simulation. Okay, and the engine I'm looking at is the envelope simulation. So when I run this simulation, again, this is my RF Pro EM simulation results. Okay, we can take a look. Again, it's the same sub-circuit that I'm using. And then once I'm done, I can run the virtual test bench. And this is some of the results that we can see. Okay, I'm just going to zoom in here because I think these are the more critical parameters that will be more interesting. So on the left, you can see that with this virtual test bench simulation, we can look at the EVM of my LTE signal with my PA. Okay, so I'm simulating at minus 30 dBm. So that's my input power from my PA. And you can see that with minus 30 dBm, you can see that there are some side lobes for my main spectrum here. So the EVM still looks okay. The constellation still looks clean. The ACLR looks okay as well. The EVM looks all good. Okay. We also have EVM pass fail flag. All right. So you can see that the EVM and the ACLR does pass the 3GPP standard here. Okay. So what will happen if I drive it to 0 dBm? Okay, what will be the performance? All right. So if I switch to the 0 dBm, okay, now I'm driving my PA with a 0 dBm input power. You can start to see that the EVM starts to worsen. It's now 16 dB, quite bad. You can look at the spectrum here. This is definitely going to cause issue for any adjacent spectrum. Okay, so probably you're going to relook at the design. You can see that the constellation starts to worsen as well. And in fact, if you look at the ACLR, it starts to fail. Okay, so this is on the virtual test bench working on the RF Pro EM circuit post simulation. Okay. So yeah, I think with that, the last part, so I think I'll share this slide after this presentation here. The slides will go through what we are doing. So I just wanted to highlight again, for the virtual test bench, I might have gone a little bit fast, but what we are doing on virtual test bench is basically sort of like having a virtual signal generator that is producing the LTE signal and having a virtual signal analyzer for you to analyze this kind of spectrum here. So that is the purpose of virtual test bench. and then we simulate it with the RF Pro EM simulation results, if you remember. Okay, so the slides will cover some of the things that we've discussed. The last part about IC design is that because sometimes when we do module design, the module will call IC chips, for example, PA, switches, and then another PA as well. So for ADS, we have the Smart Mount feature, which allows you to do multi-technology simulation. I won't go through the details, but just within a few couple of steps here, basically you can see that we can actually integrate the different technology design, right? Basically the IC substrate will have a different substrate technology with our package or our laminate module here. So basically through a simple drag and drop, we are able to combine the different IC chips together on a package and integrate it with a bond wire. Okay. So again, yeah, so just illustrate just a simple drag and drop. We are then able to combine the different designs using the bond wires. You are able to draw bond wires in ADS as well, by the way, for that connection. Okay. And then likewise, once you have completed this switch module, again, using RF Pro to do that full EM simulation. Okay. So again, the setup is the same, just through a few simple drag and drop. And then we can run the EM simulation, create that generated subcircuit, use that generated subcircuit back to our test bench to run S parameter simulation or run harmonic balance and so on. And then we can quickly look at the overall module design here. Okay, so this is on the Smart Mount technology. And if you want to do a little bit more advanced, right, because for IC, usually we want to mount it on the PCB board to do our IC testing. Okay, so this video here, there's no sound, but sort of summarizes the Smart Mount technology. Basically, you have a RFIC or MMIC or laminate that you want to integrate together. All this, you can do it in ADS, and then you can mount it on the PCB, okay, to do that simulation. You might be wondering, this 3D component, how do we create that? So that is on the next topic, which is on EM Pro. We're going to look at EM Pro on how we can actually do some 3D modeling here. Okay, but basically all this you can do within ADS environment, and you can do a full EM simulation on that for this kind of DUT test board. So I also included some videos if you're interested to find out more. Yeah, so feel free to gain access to some of our YouTube videos on that. Okay, so I think I'm done for the first part. Let me pause for a while, and also probably a good time for you to take a quick short break while I answer the Q&A before we look at the next example. Okay. So I think the first question was, could you elaborate on the potential limitation and drawbacks of using ADS software for antenna design and creation of equivalent circuits? When it comes to antenna design, I think ADS limitation would be because the layout capability of ADS only restrict on 2D drawing. So when it comes to antenna design in ADS, you are quite limited in terms of you are able to only draw planar antennas. For example, like patch antennas. So patch antennas, definitely you can do it on ADS, you can draw it on ADS, and together with the substrate properties, and then using RF Pro, that 3D structures will start to appear here. So I would say for ADS, the drawing capability will be the limitation. If you are looking into, for example, like horn antenna, definitely ADS won't be able to do it. That's where EM Pro will come in. Creation of equivalent circuit, we don't have an automated way. I would say that you can start with some reference circuit, and from there do some optimization to try to optimize that equivalent circuit to get it as close as possible to the EM simulation of the antennas. So I would say you still have to manually create that topology for that equivalent circuit, and then you can do optimization to get the equivalent circuit of ADS, for the antenna design. Okay, so I think these are some limitations when it comes to drawing the antenna for ADS. Okay, okay, but do not worry about the 3D drawing. Let's say you have some spiral antennas or helix antennas that you want to integrate it with your PCB design. ADS has the capability for you to import or integrate any 3D drawings design they have done in AM Pro and combine it with your PCB design. That will be one example we will look at, which I will talk into details later. Okay. I think the next question was, can you compare RFIC circuit performance between Golden Gate simulation and only using ADS to do all simulation? Okay. So Golden Gate is I would say a circuit simulation software that is embedded in Virtuoso environment. So what are some of the key things that I would think Golden Gate is beneficial for you is that Golden Gate does have the harmonic balance simulators. So if let's say you face any convergence issues with some other simulators in Virtuoso, definitely the Golden Gate harmonic balance simulator is one thing that you can look at. For Golden Gate, we also have some quick simulators for you to quickly look at the results. For example, like IP3 simulation, 1 dB gain compression simulation. We have some noise analysis simulation that is part of the Golden Gate bundle as well. So we do have a few simulators that is already available in Golden Gate, and you just have to specify the parameters and just run it. Golden Gate able to plot the results for you. Another key feature that I can think of for Golden Gate is virtual test bench. So Golden Gate also support the virtual test bench simulation. If you are looking at final verification stage whereby you want to simulate a 5G signal together with your PA for Golden Gate in Virtuoso environment, Golden Gate has that as well. The last thing that Golden Gate can comes in is circuit excitation. Probably I did not highlight that. Let me just go back to RF Pro very quickly. So for RF Pro, if you are looking at near field analysis, we have this circuit excitation capability. I don't think I have the results here. But what does circuit excitation do? Meaning that whatever you have simulated in this kind of harmonic balance test bench, for example, whereby you want to look at your current density flow of your design when integrating with the layout together with the circuit component. So RF Pro does have this circuit excitation performance. And the thing is that if you are, let me go back to the chat. So if you are looking, if you are already using RF Pro in Virtuoso environment, and if you are interested to look at the circuit excitation in Virtuoso environment, RF Pro, then Golden Gate can comes in for you to do circuit excitation simulation in RF Pro. Okay, so yeah, I would say these are some of the key benefits of Golden Gate that enables you, to do simulation in Virtuoso. I think there was the second part, only using ADS to do all simulation. Well, I would say that if you remember the smart mount capability, this is something that is only available in ADS. Okay, something only available in ADS. So if you have any RFIC components you want to mount it on the CAP package, in Virtuoso we have this sort of feature called send to ADS. So you can actually send your layout to ADS and do that smart mount. So this is one feature that Virtuoso does not have. We also have some stability analysis called the WS probe, which I won't go through today. If you want a comprehensive stability analysis, because when we talk about stability analysis, it's not just K factors. There are so many stability approaches out there in the industry. So the WS probe is one tool that I don't think Virtuoso has it. But within a single simulation run, you can actually look at a total of about 14 stability results within a single run with WS probe. And then of course RF Pro, now RF Pro is available in Virtuoso, in custom compiler, and it's available in ADS as well. So yeah, RF Pro is available. So I think smart mount and the stability analysis is something that Virtuoso does not have. And then the virtual test bench, if you are using Golden Gate, then that will be available. But if you are using any other circuit simulators, then you will not be able to have the virtual test bench capability. Okay, so I hope that answers your question. For next question is for EM simulation, does Keysight has another version of software for high frequencies more than 10 gigahertz than EM Pro? I would say most of the software are able to handle more than 10 gigahertz. We do have some users who are IC designers that I know of that are simulating up to, I think the highest I've seen is 40 gigahertz. So I think to address the question better is, yes, we do have some papers that simulate as high as, I think, about the more than 110 gigahertz. I think that's for the 6G application. So definitely we have simulation software that covers on that. I think it dives down to the EM engine. What kind of EM engine you're using? Is it Momentum? Is it FEM, FTDT? The tool like EM Pro, RF Pro, it depends on your application. We also have tools such as SI Pro that is done for high-speed digital. So it really depends on your application here. But definitely our EM engines is able to cover quite high frequencies. Okay, so I hope that answers your question. Okay, I will quickly just run through the next few because I think we have limited time. So does cable length affect impedance matching? So for cable length, I would say technically yes. Definitely when you start, because cables have impedance as well, right? So definitely if if there's a mismatch in impedance, definitely we need to do something to make sure that both the cable impedance and your circuit impedance, for example, have a good match. I would say circuit is probably one of them. But I think this part probably we can get back to you. I think there are other solutions out there as well. But at least for ADS point of view, circuit component sort of matching is one approach that we can look at. Okay. And then if you like to tape out, I see the DRC LVS check is important, right? Yes. So in ADS, we have the DRC and LVS. So we have the DRC that you can work on. We have the LVS as well. By the end of the day, it depends on whether you have those files from our foundries. So usually the foundries will provide DRC file and LVS file check for you to check. But definitely we have some tools that is already available for you to do this kind of root check as well. So the most important thing is make sure that you get those files from the foundries and then you can use it in ADS features. Okay. So I think I've answered those questions live. And I think due to time constraint, I better move on to the next few topics quickly. Okay. So the next topic is on rectangular design. So we will quickly look at some examples of antennas. I don't think I will dive into a lot of details, but to just show you what are some things that be done, and we can look at some of the results here. Okay. So the next product that I would like to introduce to you is EM Pro. Okay, so what is EM Pro? EM Pro is sort of the equivalent to CST or HFSS. It's really on 3D modeling. And for EM Pro, we do cover the engine of FTDT and FEM. And we have some antenna element and array designers, which I'll show you in the next slide. For quick design generation, we are able to do parameterized 3D EM co-simulation and optimization with the help of ADS as well. Okay. We recently also implement some parameter sweep within the EM Pro environment, so that is also possible. The most common use case we see with our users is that they will create 3D structures like RF shielding, for example, and they will import into ADS for their PCB design. I have one example for you later, but this is one very popular use case that we often see with our users, right? And EM Pro, likewise with ADS, both ADS and EM Pro are supported in both the Windows and Linux environment. Okay, so you can use that on that. So on the right side, there are some use case whereby you can use EM Pro for example, like phased array antennas, horn antenna, and we can also do specific absorption rate SAR simulation with EM Pro. Okay. So again, diving in a little bit, a few applications. We can do this kind of microwave and RF port as well, specific absorption rate. If you are looking at connector models, we have that as well. And if you are looking at RCS, EM Pro is able to do that too. Okay. So adding on, this is some new features that we have in EM Pro, which is the Antenna Designer Toolkit, whereby we allow you to quickly, generate the desired antenna that you want. So some of the supported designs that we have, for example, the waveguide antennas, inverted F antennas, regular patch antennas. We also have some wire antennas that we do support. So you can key in some of the parameters that you need, define the materials, and then EM Pro will actually quickly create that design for you. Okay. And then, if you are looking at phase array design, so after you have created that one element from that design toolkit, we can use the phase array antenna toolkit to actually populate that phase array for you. So some of the phase array that we do support is like cylindrical, linear, planar, and so on. So we can actually quickly create those phase array design for you. Okay, and then you can also have some pattern editor, removing some elements to see how would be the performance of your phase array design here. Okay, so these are some two new features that we added recently to EM Pro. And yeah, this is the most popular use case that we've seen among our users, is that whatever 3D designs that you create in EM Pro, you can actually seamlessly bring it into ADS. They actually share a common database here. So you just have to define the library. Everything that are designed in EM Pro will be brought into ADS, and then you can combine it with your design here. And you can, you can change the EM Pro design. Whatever changes you done in EM Pro, you will automatically update in ADS as well. Parameters created in EM Pro, you can use ADS for optimization and parameter sweep. Okay, so this is one common use case that we see among our users here. Okay, so yeah, just to highlight some of the potential use case that you could be using as well when it comes to ADS and EM Pro integration. Is that yeah, we can look at this simple example here, right? The first step is, let's say you have already a board designed for you, okay? Whether is it from Altium or Cadence Allegro or Zuken, definitely that PCB board we can import into ADS layout here. Once that's done, again, you can use RF Pro, and RF Pro is the main tool whereby we can start to do 3D import here. So this is not the actual design, it's just a proof of concept whereby I have a helix antenna and a SMA connector that I integrated together with my PCB board here. And then I use RF Pro to do the EM simulation. And if need to, I can do optimization whereby I optimize the impedance matching network. It's a little bit small here, but you can see that basically this PCB here, I sort of place two matching network element component. I think it's an inductor, also a capacitor, I think. So basically, just for proof of concept, and then after the EM simulation results, I do an optimization to get the lowest S11 at certain frequencies. I optimize the S parameter results and get this kind of results here. Okay, and then once I've done, again, I can do circuit excitation, bringing in my circuit components together with my EM simulation results and relook, after impedance matching, how would my radiation pattern look at? And also look at the near field analysis. Okay. So coming back to one of the question, right? Circuit excitation. This is what I meant. I can do a AC analysis together with my EM simulation results and my circuit components. Bring those data back into RF Pro and relook, together with the impedance matching network. How would my radiation pattern change after impedance matching? Okay, so this is what I meant by circuit excitation. Okay. So I will just quickly dive into looking at antenna design EM Pro and how you can integrate it with a rectifier circuit in ADS. Okay. So yeah, what you are seeing here is a patch antenna that I created using EM Pro. Okay, so we're now looking at EM Pro software. So EM Pro software have some building blocks that you can create this design here, which I've already done. Okay, so this is just a simple patch antennas that I've used for this kind of drawing tools. It gives you a 3D view, and then I have a ground plane at the bottom of my patch antennas as well. So all these I've already, defined materials, so you can define your own materials for the simulation. And then I also have some ports excitation as well to characterize this patch antennas here. As mentioned earlier, FDM engine is one of the main engine that EM Pro supports, but we do support the FTTT simulation as well. One thing to take note is that for you to integrate EM Pro design together with ADS, the main engine to use is FDM. Okay, FDM engine. This is the main engine that helps to unite the EM simulation between ADS and EM Pro. Okay, what are some of the results that you can look at? For example, I think I've already prepared the results here. Definitely you can look at the S11 results. Okay, so the resonant frequencies of this antenna here is about 2.475 gigahertz. This is the main frequencies that we're going to work with, and we're going to do impedance matching together with the rectifier circuit. Okay, so we can look at S11, we can look at the Smith chart, and then measure the impedance at this frequency. We can look at 2D cuts as well. So this is one cut that we are looking at. And then we can also look at another theta cut. Okay, phi cut, sorry, this is not phi cut. Okay, so we can do 2D cut as well. If you're interested to look at the radiation, we can look at the gain. So this will actually show you the radiation pattern of your patch antenna. So we are looking at 2.475 gig. So this is the radiation pattern of my patch antenna. And we can look at statistics, for example, what is the radiation efficiencies. We can also look at other statistics such as the maximum gain and so on. Okay. We can also look at the near field sensor. I don't think I have the results ready, but if you are interested to look at how the current density or how the current is flowing across the patch antennas, we can actually place near field sensors and do that measurement. Okay, I think I have that results ready. Let me see if I can able to plot it for you. Yeah, I think I have that results ready. Okay, so you can place the sensors here, and I think we are looking at 2.475. Okay, and then you can start to look at how the current is flowing. Okay, I think I turned on too much materials. I think let's just look at the sensors. Okay. Yeah. Okay, so you can look at some current plots here. Okay. These are some of the results that you can look at with EM Pro simulation here. Pretty standard as compared to the other 3D EM simulation tools, I believe. Okay. Okay, the next thing is, okay, you are done designing the antenna design. Then the next thing is we're going to look at the rectifier circuit design here. Okay, so let me just close this workspace here. And then we're going to look at the rectifier design here. Okay, so as an initial design of my rectifier design, you can see here basically this is the schematic setup that I have. I actually brought in some Schottky diode models that ADS already have. If you have models from vendor components that you want to bring in, for example, if you look at the left, there are some Murata components that you can bring it in as well. Okay, so this is the Murata library that I brought in into ADS. So I've already created this doubler circuit for my rectifier design, and this is the input power that could be received from the patch antenna here. Okay, so basically the impedance I measured from EM Pro, I brought it in as well. And then these two are my matching network. Again, I'm using the Smith chart utility tool to help me do that impedance matching. Okay, so the first step is I do an S parameter simulation to sort of understand what is the impedance, the input impedance of my rectifier. And from there, I do impedance matching for my antenna impedance and my input impedance for my rectifier. And this is how I actually create the impedance matching network. Okay. So again, very similar to the amplifier design that I shared earlier on. The circuit design is done, and then we can look at the results. So this, I think I have the results here. Uh, so this is the initial, very ideal, just lump components, no microstrip. We can see that the red curve shows the input 2.475 gigahertz waveform measured at the output, at the input, but the blue plot shows the rectified voltage at the output here. Okay, so you can see that we actually get a DC results here. And then the next step, what I've done is, moving into transmission line. Okay, so again, I add in some transmission line here, okay, and see how the transmission line will affect the results here. So definitely adding on the transmission line, definitely results are going to shift, resonance is going to shift, impedance matching network is going to shift, and that's where I use optimization to help me to fine tune and make sure that I get a good match at 2.47 gigahertz. Okay, and then again, we can look at the results with the microstrip line. Okay, definitely you can see as I increase the input power, there's going to be some ripples coming in as well, which is kind of expected now that we have some transmission line included to it. And this is after I've done optimization, still making sure that my impedance matching at S1, DB-S11 is still at a good match at this frequency here. Okay, same flow. Once I finish creating the layout, or sorry, the schematic, again, I can do design synchronization to, bring everything I've designed in my schematic level. I want to make sure that my components, the components values are not changed, all right? So I do a design synchronization, and then this is where I created the layout here. Again, this design is just a proof of concept. It's not the actual Rectana design. It's just to show the workflow between ADS and EM Pro. Okay. So this is the layout I have created. You can see that I have my circuit components already all created for that. And then that's where I can start to use RF Pro to do the EM simulation. So again, the setup is very simple. Drag and drop, set up the ports, define which one is ground net. So P2 is actually my ground net. Okay. If I take a look, P2 is actually my ground nets, okay, together with the vias, and then P1 and P3 are my my signal nets for some of the input power connection and to my load as well. Okay, so yeah, again, the setup is very simple. Set up the component models, and once the simulation is done, we can quickly generate a sub-circuit. Okay, and then we can start to combine it with a test bench here. Okay, so this is again the same workflow as you understand earlier on with the MMIC application. This is a sub-circuit which contain my EM simulation results. If I dive into it, you can see that it's the same thing, right? Whatever circuit components that I have defined earlier on, everything is connected automatically for you. Okay, you don't have to do any modification. And I also wanted to highlight that you can do tuning with that EM simulation results. So you can see this T here. Basically, previously I was doing some tuning to fine-tune the results. Okay, so I actually fine-tuned my capacitors and inductors together with my EM simulation results. And then I rerun the simulation again to get this results here. Okay, so again, with the EM simulation results, definitely there's going to be more ripples coming in when the input power increases. Okay, so that's on the rectifier design. The last step is combining, my antenna design together with my rectifier design here. So again, let me just quickly take RF Pro out. So what you see here is my patch antenna that I've designed earlier on with EM Pro. It is now nicely integrated together with my rectifier circuit here. Okay, so basically, how do I do that? I remember the shared library that ADS have together with EM Pro. Once you bring it that shared library, we have this insert EM Pro 3D component that is able for you to combine it with your PCB design here, for example. Okay. And then again, the port setup is very simple, just do simple drag and drop. The port setup will be defined for you, the circuit components will be defined for you, and then you can start to run the EM simulation. So again, the workflow is the same as what I've gone through earlier for the amplifier design, the setup for EM simulation. Okay. And then once that's done, again, we can generate the sub-circuit, and then we can do a test bench simulation. Okay, so what I'm simulating is sort of like a modeling of the input power received by the antenna, and now together with the antenna with all those potential coupling effects that could be coming across with your PCB board. Again, how would the results changes, right? So this is the full rectangular design. Now we place in some input power. Again, it's connected automatically together with my circuit components. So you don't have to do anything. Just connect it with the test bench. We run the simulation, and I think this is the final results that I have. Again, I did some fine tuning as well because after placing the antennas, the results got a bit off. It wasn't very perfect. So I have to do some fine tuning to some of the components and eventually getting a great output voltage about 3 volts. Okay. So I think this rectangle could be a potential IoT application or energy harvesting application. So we do have some papers as well on some of the universities or even the commercial companies that use ADS for energy harvesting circuit analysis here. So if you're interested, do let us know. We can share the paper with you. Okay, so this is on the rectangle, and hopefully it gives you an understanding on how you can do antenna design. Patch antenna is just a simple example here, but to show you what are some of the results that you can look at. Okay. Before I end off this rectangle design, I thought it would be good to share with you. This is a video that is done by InnoWave, one of our customers. So Dr. Prakash actually did a demo on how an helix antenna can be integrated with a PCB design done in ADS. So this is an existing use case done by our customer. I have provided the YouTube link, so do feel free to check out this video here. He actually done a great demo to show you how you can create a helix antenna in EM Pro, how you can bring it into ADS and do impedance matching together with the helix antenna here. So I highly recommend you to look at this video here. And then another example is the application note testimony. I think it's done by Seiko, whereby the customer actually has a large PCB board that contains both the digital and the RF signal here. And the purpose of this use case is that he wanted to investigate, how well can this EM 3D shielding shield off the digital signal here. Okay, so what he does is he actually do a specific net analysis of this portion of this board here. He didn't do the full EM, right? He just used RF Pro, specify what he only needs to simulate, which is only this portion here. He used EM Pro to create the 3D shielding and mount it nicely on the PCB board. Once he completed that EM simulation, he generate that sub-circuit here, which you see right here, and then he do a RF and digital signal simulation. So this is the RF signal, which is on DBB signal. I think he has a custom waveform that he wants to simulate. So this is his custom waveform that he brought it into his simulation. And this is the digital signal waveform that is coming from the board as well. Okay, so after which, he does a comparison. The red curve here shows that, together with the digital interference, the RF signal is the main signal that they want to measure. So initially there was a digital interference over here, and then now with the incorporation or together with the 3D shield that you see right here, the blue curve shows that the digital interference has been removed. So this is one example use case for EM Pro and ADS integration. Okay. Let me see if there's any question. Okay, so far no questions. So yeah, I think this is the last part. that shows EM Pro capability when it comes to EMI and EMC simulation. And today's quick demo is just to show you on both EMI, EMC, that could be, we can do a rack mount chassis investigation to look at the EMC and EMI performance of this chassis here. Okay, so this is the last part. Okay, so let's take a look. So the first one we're going to look at is, I think, is EMC, which is on, we're going to look at the plane wave excitation here. So this is the full chassis design here. And if I open this up, basically you can see that I have a high-speed digital board here. It's a very simplified model. The main use case is to see how well this chassis here is able to reduce interference or reduce emission here. That's the main purpose, all right? What I've done here is I've done a power plane. This is my main interest of area to see how much of interference can be detected using plane wave excitation here. Okay, so this is the main area that I'm looking at. And then what I've done is I've indicated some excitation here. Okay, so one of the excitation that I've done is based on phi 90 degree, and the theta is actually about 45 degrees. So if I make use of this axis here, okay, sorry, let me just revert, all right? So if I'm simulating at say phi minus 90, so it's the negative y direction, and minus 45. So basically the excitation is coming diagonally towards this board here. I also have another excitation which is on minus 90 degree, the negative y direction, and also minus theta here. So it's coming from basically just the minus y direction here. Okay, and then yeah, so basically this will be the external excitation that we'll be doing. And then basically the excitation, we are looking at a broadband signal that is on at a frequency of 3 gigahertz here. Okay, so I'm doing this excitation. And then yeah, after that we are looking at FDDT simulation to do this plane wave excitation here. And once I finish the simulation, some of the results that I can look at is, for example, what would be the detected spectrum, for my power plane board. So this is one result that I can look at. Basically, the blue curve shows the theta equals to 90, phi equals to 90 plane wave excitation, slightly lower spectrum. But if I compare it with the theta 45 and phi minus 90, you can see that there's a high spike spectrum that is being detected. So this is something that we might want to look at. So it's really for investigation stage to see how well that chassis is able to block off any potential interference. Okay. So this is one result that I can look at. I can also change the polarization of my excitation. So this is on E theta, right? The theta polarization. I can switch to phi polarization and kind of look at how the results changes. So I've already plot that out. The same excitation but different polarization. You can see that now the theta 90 and phi minus 90 sort of have a higher peak now, okay, for the interference. Okay. So yeah, this is one example of how you can see how well the chassis is able to reject any interference here. We can also look at some of the visualization. Okay, so we can look at this excitation here and look at how some of the radiation is coming from the chassis here. Okay, so what I'm going to do is I'm going to give you a visualization and sort of adjust the maximum to have you have clearer. So you can do this kind of current density or excitation visualization plot to kind of understand how the radiation or the EM waves are propagating across the chassis as well. So this is one example that you can look at. Okay, but I think for this kind of plane wave excitation, the key parameter is really to look at how much interference we are detecting and how well that chassis is actually blocking those interference. Okay. So this is on the EMC portion. Hopefully it gives you a quick view of what are some potential use case that you can work with EM Pro. So this is on the EMC part. The next part is on EMI, right? How much emission is being produced for this design here. So we can use back this same design here. And the main interest is this differential line pair. Okay, so what I've set up here is my ports here. This is where my main signal will come in. And then I have terminated with a 50 ohms load here. Okay, so for the signal source here, EM Pro allows you to import your own custom waveform. So for this, since it's a digital signal, I'm interested to look at differential and common mode signal. You know, how would the emission be, for example? So I can bring in my custom waveform as well and bring in this kind of digital waveform. So this is the time domain and the frequency domain of my digital waveform. And I'm going to use this waveform here to excite this differential transmission line and see how much emission is able to create. Okay. So with that, I can first perform the simulation. Take note about that. I think I disabled it, but this simulation does include this chassis cover as well. Okay. And then we can run the simulation. And after finishing this FTDD simulation, okay, I'm running this FTDD simulation. EM Pro have the EM emission calculation for you to do your EMI emission spectrum analysis here. So I'm using my FTDD results, and then, you know, I can specify my waveform that I'm using. And since I'm interested in the differential mode and common mode, so to do that differential mode analysis, I can specify the amplitude multiplier. So this is, you know, the negative portion, and this is the positive portion for my differential pair. And then the next thing is the plotting option, right? You can define whether you want to look at specific location or E-field or over location. Okay, so basically, I think when it comes to radiated EMI, we want to look at probably a specific location that you can define. But if you're interested for all location, that is all right as well. And then we are going to be looking at 3 meters. That is one of the FCC standards here. Once that's done, we can actually plot the results, which I've already done. Okay, so we can take a look at the results here. Okay, so this is the results here. Basically, we are comparing with the FCC standard here. So for EM Pro, we already have some EMI mask. If you're looking at CISPA 25, we have that as well. If you're looking at some military standards, we have that as well. So we can include some of these limits and kind of understand, you know, whether your design does it comply to some of the commercial standards here. So as expected, right, for common mode signal noise, definitely it has a higher spectrum emission as compared to the differential mode. Okay, so this is one analysis that we can look at. And then sometimes some designers might be wondering, what if I have a slot plane right here? Meaning that, okay, I've already simulated that. Let me just show you. What if, you know, my ground plane here, I added a slot here? How would that affect my EMI performance, right? So again, the same step, you know, we can modify the design using some Boolean operation to modify that design here and create this slot. If you see this hole here, this is the slot design. And then we can rerun the FTDD simulation, and then we perform the emission calculation and take a look at the spectrum here. So I've already done that, and we can look at the results here. Now you can see with that slot design, definitely you can see that just with the slot design, it's going to affect your interference. There's more emission now. But yeah, you know, it still comply with the FCC standards here. And again, as expected, the common mode noise will definitely has a higher emission as compared to your differential mode noise. Okay. So yeah, I think this concludes my EMI EMC demo for EM Pro. Just a simple illustration of some of the use case that you can work with for EMI, EMC simulation with EM Pro, measuring, the emission and also doing plane wave excitation. Okay. Before I end off, just to let you know, EM Pro is not the only solution we have for EMI, EMC. All right. I just wanted to highlight, if you are designing power electronics devices like DC-DC converters, phase shift inverters, we have PE Pro, which is specially catered um, for power electronics. With PE Pro, we have test bench that quickly allows you to do conducted and radiated EMI, and we have this kind of templates for CISPA 25. So this is on the PE Pro. If you're working on that, if you want to find out more, do let us know. Yeah, we can do circuit excitation as well for your converter design. Okay. So yeah, we are able to do conducted EMI, connecting with some of the LISIN modules that is part of the conducted EMI, and then look at some of the, whether does it meet the CISPA 25 standard. So this is on PE Pro. Radiated EMI, this is also covered in PE Pro as well. Okay, so for the different pros product that you will see, basically it still function on FEM and momentum engine. All right, so you see RF Pro, PE Pro. Later I'll go through with you on PI Pro. They still function more towards momentum and FEM. Only for EM Pro is based on FEM and FTDT. Okay, so these are some of the EM engines that we do support here. Okay, so if you are looking at power electronics, we have PE Pro. If you are looking at high-speed digital boards, right, looking at power distribution network, DCI drop, we have PI Pro. And PI Pro, we are also able to do conducted EMI and radiated EMI. So for high-speed board, basically we are talking about many substrate layers, about 16 layers and so on. So if you're working on high-speed digital boards, we have PI Pro to help accelerate that EM simulation. And again, you can look at conducted EMI and radiated EMI. Okay, again, all the pros that we have, PE Pro, RF Pro, SI Pro, PI Pro, they are all based on this kind of quick generation of sub-circuit. So you don't have to do any manual connection with your EM simulation results. All this can be done very quickly for you. And then you can look at this kind of CISPA 25 results. Okay, and then radiated, PI Pro, you can actually rotate the orientation of the PCB and sort of look at the different spectrum here as well. Okay, so we have solutions for EMI for high-speed digital boards as well. Okay, I think that's some sort of conclusion. Let me just run through the conclusions first before I look at the chat and Q&A, all right? So to sum it off, I think just nice, 1 hour 45 minutes. So in summary, I think ADS provides an efficient and accurate EM circuit simulation. We discussed a lot about RF Pro. So RF Pro is the main tool that I really want you to bring home today and remember the key values of RF Pro, how RF Pro can really help you to be efficient and effective when it comes to EM circuit co-simulation design. Okay. And then we also went through about EM Pro, how EM Pro can do 3D modeling EM simulation. We talk about EMI, EMC, antenna design, quick generation of antenna elements, and also phase array design. If you're looking into that, we have solutions for that. And the last thing as well, I want you to remember is how you can actually integrate 3D components together with your PCB design and really do a full 3D EM circuit co-simulation and providing you many great designs inside before you produce your product here. Okay, and again, the last part, just to sum it off, for Keysight simulation software, we cover a wide range of application. Do talk to us if you have any other applications that you are wondering if we have solutions for that. Okay, so thank you very much for your time.